going into the second hour now of fluids for Physics 1B. We just discussed variation of pressure with depth. You should be able to do some homework problems with that. The next thing we want to talk about is Pascal's law. Okay, and Pascal's law, the thing that we want to understand here is basically how something like this works. Hydraulic lift, something you may have seen in a or used in a an automobile shop getting your car worked on or something like that. So this is based on something that's called Pascal's Principle, and I'm going to write it out so that it's a little bit clearer than me typing, because it's kind of long-winded. Can't type right now. Okay. Pascal's Principle states that any change in pressure for an enclosed fluid is transmitted undiminished to the entire fluid. Undiminished. Okay, so what does that mean? What that means is suppose that you have a system that has an enclosed fluid in it. So that could be something, let's say, like this. So let's say you have something where you've got like a vessel, and contained in this vessel you have air, and in order to prevent the air from escaping, you fix some kind of piston into the system here that is free to move up and down, but does not let the air escape. So you have a little piston right here, right? And you've got a handle on it so you can push it up and down, right? And inside of here you just have air. All right. If you were to push down on the top of this with some kind of a force, that force is going to have the effect of increasing the pressure not just at the top, but throughout the entire system. Okay? Another example would be if you have a balloon and you squeeze the balloon, it's going to increase the pressure not just where your hands are, but throughout the entire balloon. The whole balloon is going to feel that pressure, right? And you'll see it because the balloon will deform in some way to adjust to the pressure change, right? So one application of this idea is a hydraulic press. All right? And in a hydraulic press, you have one specific change here, which is that the fluid that you have in here needs to be what we call incompressible. So air is something where if I push down with a force, I can force a piston down, and I can reduce the volume of air that's here, which will then increase the pressure, right? Because you have a bunch of air molecules. If they don't escape, if you reduce the volume, the pressure has to go up, right? In the case of a hydraulic press, we're going to be talking about a system in which the fluid is what we call incompressible, or very, very nearly incompressible. So an example of something like this would be like oil or water. If you put oil or water into a system like this, then what you can do is, for a very small force, you can lift very large objects. So let's just generally talk about kind of how a system like this works. So I'm going to draw kind of a picture of this here. Do I need to draw a picture? This picture's pretty good, actually. So in this picture, what you have is you have a hydraulic lift on one side. It has a car on top of it. There's a piston that can move up and down here, and a piston that can move up and down here. The only difference between the pistons is that one of them has a smaller area than the other one. Otherwise, they're both shaped kind of similarly. On the left, you push down with the force on the left side, and it causes the car to rise up on the right side. Not as far as you push down, but it rises up nonetheless. Now, within this system right here, in the brown area here, the tan area here, if that fluid is incompressible, the additional force here, according to Pascal's principle, should change the pressure of the fluid, which will then affect the pressure over here. And if you increase the pressure of the fluid, it'll force this side to go up. The main thing is that within the system, that pressure has to be constant. So if the additional pressure that you put into the fluid over here ends up being equal to, well, we said that pressure was force over area, right? So if I take the force on the left-hand side and I divide by the area, that same increase in pressure, you could call this a change in pressure if you want to. I'm not going to do that, but you could, that's effectively what you're doing, because initially maybe the pressure of the liquid in here is at 3 atmospheres. We're introducing additional pressure, but that's what Pascal's principle is about. It's about a change in pressure. So I guess it is appropriate to just put that delta P there. I think sometimes this can confuse people. The point is, we're increasing the pressure by this much, so on the right-hand side, you're going to get an additional force that corresponds to that same amount of pressure. And if we rearrange this system right here, then we'll see something pretty clearly, which is that the size of the force F1 that you actually need to lift the car ends up being equal to the area A1 divided by the area A2, and you take that ratio and you multiply by the force on the left-hand side. So what this allows us to do is it allows us to lift a car with a very small force, depending on what this ratio is right here. For example, if the force that we wanted to place on the left-hand side was a force of, let's say, 10 newtons, and if area 1, let's just say, for simplicity's sake, we call 1 unit of area, and if area 2 has a unit of area that's 10, right, then we could actually reverse this so that it looks something like this: A2 over A1 times F1 equals F2. And if we plug in the numbers we have here, if the force that we place on the left-hand side is 10 newtons, and area 2 is a factor of 10 larger than area 1, then we get an amplification of force for the other side of a factor of 10, right? So for a force of 10 newtons on the left, you get 100 newtons on the right. And then by making this ratio even more extreme, you can lift even bigger objects. Okay? And that's kind of the principle behind how a hydraulic lift works. Maybe some of you guys have hydraulic lifts in your, like, to jack up your cars. Or maybe you've used one at a service station before, or a mechanic shop. Anyway, does that make sense to you guys? Do you have any questions? We're going to do this problem right here. So in this problem, in a similar scenario to the one above, you have a compressed air that exerts a force on a small piston that has a circular cross-section and a radius of 5 centimeters. The pressure is transmitted by a liquid to a piston that has a radius of 15 centimeters. What must the force of the compressed air to lift a car weighing 13,300 newtons? So someone's typing something. I'll let them finish typing and then... Yeah, sure, no problem, man. I can make that bigger. Is that more legible? Okay. So, so our system now is going to be, one side we have a circular cross-section that has a radius, I'm going to call it R1, that's equal to 5 centimeters. It's the radius of this piston over here. And it's connected to some type of an incompressible fluid, like this. And on the other side, you've got a much bigger system over here. And this one has a radius that we call R2. And we're going to say that one's equal to 15 centimeters. And sitting on top of this one, we've got a car. So we've got a car sitting here. And this car has a weight. I don't think the yellow is going to show up very well. The weight of the car we call W. And it's given in the problem here. That's the weight. And then the idea is that there's going to be a pressure increase because we're going to exert a force down on this side over here. And it's going to produce a corresponding force on the other side, pointing back up this way. And we want that force on the right-hand side, F2, to at least be equal to the weight of the car. All right? And we want to just figure out what is that force equal to. All right, so yeah, let's figure out how this works out then. So we said before that the pressure has to be the same throughout this entire thing. The pressure is a constant. And we can say that on the left-hand side, our pressure is going to be F1 divided by the area of the left-hand side. On the right-hand side, the pressure is going to be F2 divided by the area over there. We can rearrange this one to solve for F1 and say F1 is going to be equal to the area 1 on the left. This is going to be A1 divided by area 2 multiplied by force 2. How do I find area 1? What would the area of a cylindrical piston that has a radius of 5 centimeters be? Not exactly. You're not wrong that we don't technically need to find it, but let's just keep it simple for a second. What is the area area 1? What is that going to be? How can I write that down? If I know that it's a cylindrical piston over here. Yeah, just pi r squared, right? So area 1 is going to be pi times r1 squared. Area 2 is going to be pi times r2 squared. And we multiply that by the force, right? F2. So you're close, Ed. It's not the ratio of the radii, right? It's the ratio of the square of the radii. That's the only thing I was taking issue with. But you're technically right. We don't really need to put it, right? Okay. So let's solve this. The pi's cancel out, so we end up getting r1 was 5 centimeters. And then R2 is 15. And then F2 is 13,300. And that's going to give us an answer. 418. 1480, I think sounds right. Yeah. It's a factor of 9, right? Because 5 over 15 would be 1 over 3, and you square it, so it's 1 over 9. So if you think about hydraulic lift systems that you may have seen before, the pistons are very small, right? I mean, they're much smaller than 5 centimeters, right? They may be as small as like 1 centimeter. If you think about what would happen, if you change this to 1 centimeter right here, right? So if instead you were doing 1 divided by 15, and then you had to square that, and then multiply by 13,300, I mean, you would reduce the force that you need to push to lift the car by a factor of 15 squared, which is like 225 or something like that, right? Almost 250 reduction in this number right here. So you can see the power of something like this, right? Hydraulics are extremely powerful for lifting cars. That's why we use them. Just by the action of having there's a few things that have to happen from an engineering perspective, right? Like the liquid has to not leak out, right? If the liquid leaks out in any way, you're gonna have problems, right? Something someone mentioned earlier in my class this morning was that if you use water, it doesn't work very well because the water can tend to corrode the system because it's really reactive. So if you just use something like oil and you seal it off and you make sure no bubbles get into the oil, a system like this works really well for lifting really heavy objects. So that shows you some kind of one of the powers of pressure, and specifically this concept called Pascal's principle. Okay, does anyone have any questions? Okay. Let's keep going then. The rest of tonight's lecture is going to be about buoyancy. So we've gotten through number 1, 2, 3, and 4. I think, Emily, you're hot micing a little bit. Just be careful. Maybe moving the laptop or something. Okay, so the rest of the class is going to be about this, about buoyancy. Buoyancy is a force that's related to floating. Okay? All right, so let's talk about buoyancy. Okay, so buoyancy is a force. I gotta sit closer so you guys can hear me, okay? So buoyancy is a force. and it's exerted on any object that is partially or underwater in any way. Well, it doesn't have to be water; it could be any fluid. Force exerted by a fluid on an object. It's a very vague thing to say, because we've been talking about pressure, and pressure can exert forces, and well, this is produced in the exact same way, as it turns out. This is a result of pressure differences. So, let me drag the picture real quick. This one. So, let's just look at this picture right here. So this picture displays a cube that's inside of water. The cube has a height h, and it's saying that there's going to be two forces exerted on this cube. All right, there's a buoyant force that pushes upwards, and there's the force of gravity that pushes downwards. It says the buoyant force is on the cube is the resultant of the forces exerted on its top and bottom faces by the liquid. This is because at the bottom down here, at the bottom of the cube, the pressure is larger than the pressure at the top, and so that pressure differential produces this thing that we call buoyancy. So we can go through and figure out exactly the size of that buoyant force, because we know what that pressure difference is, right? So consider a system that we've already really looked at. We take a vessel, we fill it with water, we take our object, in this case, which is a cube. I'm just going to draw a cylinder probably. So we draw a cylinder inside of this. We say our cylinder has an area on top that's A, and then an area on bottom, same thing. And we say it has a height h, and we say it's going to have a weight w, right? We know that the pressure at the bottom here we can define to be, let's say, P1. We can define the pressure at the top here to be P sub 2. And we know that there's a force on top, then, that's equal to P2 times A. There's a force on the bottom that's larger, that's equal to P1 times A. And of course, this object is subject to weight as well. In order to understand what the buoyant force is, we basically say that buoyant force is produced by the other two pressures right here, okay? So we're going to define the buoyant force to be equal to the difference in pressures, so that would be pressure 1 minus pressure 2 multiplied by the area A. But we already know what this pressure differential is, right? It's related to the height h. This is one of the first things we did in class today. From the variation of pressure with depth, we know that the difference in pressure, P1 minus P2, is equal to rho times G times H. By plugging that in here, we get this expression. And in this case, we get this H times A thing shows up here again, but we can remember that H times A is equal to what? What is the height of the object times the cross-sectional area equal to if it's a cylinder? Yep, the volume. So normally the way this is written then is that the buoyant force is equal to rho, and we put the V first usually, multiplied by G. Rho Vg. That's kind of the definition of the buoyant force. It's the buoyant force for full submersion. Okay? You take the volume of your object, you multiply by the density of the object, and then you multiply by the acceleration due to gravity. Now, Archimedes came up with a more generalized way of saying this that will apply to an object that's fully submerged as well as an object that's only partially submerged. And that is what we call Archimedes Principle. So Archimedes' principle states that the buoyant force that's exerted on an object is given by the weight of the water displaced by the object. Now, is this something I need to make larger so you guys can see better? just like usually write it like this. I think his name is Archimedes. So the buoyant force is given by the weight of the water displaced by the object. And really, water is the wrong word. I should generalize this. It's really fluid. Because you feel a buoyant force when you're in air as well. That's how things like helium balloons can float. Obviously things like volleyballs float in water, wood floats in water, certain things sink in water, right? And we'll talk about why that is. But this is what the value of the buoyant force is here. Now, what the object actually does, okay, in terms of whether it floats or sinks once it's fully submerged in the water, what's going to determine that? If the buoyant force is less than the weight, what's the object going to do? Like, if the buoyant force is smaller than the weight of the object, what's going to happen? It's going to sink. And vice versa, if the buoyant force ends up being bigger than the weight of the object, in the case of styrofoam or wood or something like that, it'll float, right? And there's also the case where they can be equal to each other. I've got another little picture here. So this is kind of an image to show those two possibilities. In the case where the buoyant force is less than, or is bigger than the weight, in the case of wood, you get an upward acceleration. It's going to accelerate upwards. And this apparently occurs when the density of the object is less than the density of the fluid. So if wood is less dense than water, it's going to float up. If you have a metal and it's more dense than water, so that the weight is bigger than the buoyant force, the object's going to accelerate downwards. And this is the case when something's floating. We'll do that case in a second. Now, what if we want to find the acceleration of the object? Or what if we want to understand these relationships here and why its density? Well, we can do that pretty simply by considering either one of these situations right here. Let's start off by assuming that B is bigger than FG. Okay? We could say, okay, looking at that piece of wood right there, we could write down this expression. We could say the net force acting on the wood should be equal to the mass of the object times its acceleration. The two forces acting here are the buoyant force and the weight. So I would just say the buoyant force minus the weight of the object, force of gravity, should be equal to the mass of the object times acceleration. We just saw that if the object is fully submerged, that this buoyant force right here is going to be equal to the density. I want to be really clear here. This is the density of the fluid. It's the density of the fluid. So the buoyant force is the density of the fluid. We'll just put a symbol F for that. Times the volume. If the object is completely submerged, just the volume of the object right here, multiplied by gravity. And then we have to subtract from that the force of gravity. What is that? Well, that's mass times gravity, right? But ultimately, we want to relate this back to density. So what we'll do is we'll say, leave this part the same. So we leave density of the fluid, volume. I don't want to keep writing OBJ. I'm just going to write volume of objects times gravity minus mass. The mass of our object can be given as basically just the density of the object multiplied by the volume of the object and then multiplied by gravity. Right? So this becomes the density of our object times the volume of the object multiplied by gravity. And then on the right-hand side, we put the same thing in. Oh, this is not quite right. This G shouldn't be here. I'm sorry about that. The mass is just density times volume. Uh-oh. I can't switch. I've done something. Okay, we're just gonna do this for now. So I don't know what I did. Okay, density times volume, right? So on the right-hand side, we have mass times acceleration, so that's density of the object times the volume of the object, and then times A, right? A lot of subscripts. I know that can be very confusing, but there's a volume in every single term. The left-hand side can be simplified like this. You have the density of the fluid minus the density of the object multiplied by gravity. Let's scroll down just a little bit here. And then if we divide that by the density of the object, that's equal to the acceleration that you get. Okay? That's kind of the relationship to determine what's going to happen in terms of floating and sinking. So, the way it's written over here, if the density of the object is less than the density of the fluid, that's basically going to mean that this quantity is a positive quantity, right? So what is that? Object is less dense than fluid. What happens? Does it sink or does it float? It's wood, right? So it should be easy to tell this floats, right? If the density of the object is greater than the density of the fluid, what happens to the sign of the acceleration then? So if this is bigger than this, it becomes negative, which means it sinks, right? Negative acceleration. Okay, what about the other? What's the other possibility that I left out? They're equal. That's right. Does anyone know what happens if the density of the object is exactly the same as the density of the fluid, or really close to it? What A becomes what? Stays in one place. It'll stay where you put it. What is that? What do that people think? Suspended. So the acceleration is 0 for sure, right? What do we know about objects that have an acceleration of 0? What do we learn in Physics 1A about objects that have an acceleration of 0? What is constant? Something is constant. When the acceleration is 0, there's something else that becomes constant. Speed. Yeah. The velocity is constant. Yeah, exactly. That's right. So that means that one of the things you guys said is true. It's possible that if I place an object with neutral buoyancy into a fluid... I'm sorry, I should have said... We call this neutral buoyancy. If you place an object that has a very close density to water, and you put it in water, and you just put it there very gently and just let go, if you're careful enough, it'll just stay in place, right? But if you even push it just a little bit, it's going to zip off in one direction and move kind of at a constant speed, neglecting drag and stuff like that. But if it moves slow enough, it's basically just going to kind of float off almost like it's weightless. Like, almost exactly like it's weightless. One of the students in my morning class mentioned that this is one of the ways that they help train people for weightlessness before they go up to the International Space Station, or for anytime they're in space, is they'll have them get into a pool. You put on and those of you who have been scuba diving may have done this before. If you get into a tank of water, you go under the water, right? And you've got this big scuba tank on you that's filled with air. That's going to change your own personal density, effectively. And what you can do to reach neutral buoyancy is they use these little weight belts. So by adding weight to your belt, and by changing the weight of that, you can make it so that you are effectively neutrally buoyant. And when you do that, you can feel weightless while you're in the water. And that's pretty powerful. Okay, I got a question that said, why do we use the floating force? Well, just because it's a force that's produced by fluids, and it's important to understand in that sense. Anything that's in a fluid is going to feel this force, and you kind of understand how it works. That's why we're talking about it. Okay. Okay, do you guys have any questions about buoyancy? We're gonna do some problems, of course, to understand this, and we'll start off by talking about a problem where an object is fully submerged, and then we'll move to an object that's not fully submerged. But only neutrally buoyant at one depth. So that's that's a great question, Travis. I'm glad you asked that, because that's something I was thinking too. So if you look at the way this works, right? I picked 2 arbitrary points, right? And it's about the pressure difference between these 2 points that produces buoyancy, yeah? And included within our discussion, we talked about area, right? But then the area kind of went away, and it turns out that buoyant force is really totally just dependent upon your volume, actually. And that's what Archimedes figured out, is it doesn't matter the shape, it doesn't matter where you are in the water, you're still going to experience the same buoyancy, assuming that the density of the fluid doesn't change over the depth you're looking at. if the fluid gets more dense the deeper you go, well, what would that do to your buoyancy? What if the water was just a lot denser down here? Maybe there's a bunch of salt down here, and there's a lot of fresh water sitting on top of it. I don't think that would happen. It kind of could, I guess. So what if there's a bunch of salt water at the bottom, and it's denser? Well, then, as you get down into that denser water, you're going to have more buoyancy, right? I mean, one thing I left out of this that maybe you guys know is if you go into a pool and you try to just float on your back, right? I can't do this. If I go into a freshwater pool and I try to float, I'll just sink. My legs will fall down, my body will fall down. But if I go into the ocean is denser than freshwater, right? There's salts and stuff in it, so it's denser. And so it's easier to float in salt water, right? But to specifically answer your question, Travis, it doesn't matter as long as the density is constant. Does that make sense? Yeah, that's pretty cool. Okay, so... Oh, this is the question I was going to ask you guys. It's still here. I thought, okay. I was clearing out... All right, this is all the stuff we're going to be doing next, but I want to actually work it out. We'll use the picture that I've already drawn there, though. It'll save us a little bit of time. Oh my god, I thought I deleted all these notes. Apparently I did not. Alright, so this is the question I want you guys to think about. And I think I put the question over here. Here it is. So suppose that I have the following scenario. So I've got a pool. Let's say it's a pool. And in this pool, I've got a beach ball, and I've got a bowling ball. Now, the bowling ball is just sitting on the bottom of the pool, doing what it would normally do because a bowling ball is obviously more dense than water. It's not going to float in water. But a beach ball, on the other hand, definitely floats in water, right? So I've got a beach ball over here. It's filled with air. The two objects have exactly the same volume, okay? And in order to keep the beach ball underneath the water, we attach a cord to the beach ball so that it stays under the water, okay? Does that make sense? You guys have certainly, some of you have probably tried this before. You take like a volleyball, or you take a beach ball and you try to push it underneath the water, what happens? It pops right back out of the water. And it's very hard, the bigger the ball is, it gets harder and harder to take that ball and push it underneath the water, right? But we could force it to stay fully submerged in the water as long as we tie a cord right here. And so the question I want you guys to think about to understand something about buoyancy is which of these two objects is going to experience a larger buoyant force, okay? So just take some time and think about it. Some of you guys are already answering, that's fine. Is it the beach ball? Is it the bowling ball? Do they experience the same buoyant force, or is there not enough information? What do you guys think? And if you're confident in your answer, you can maybe even say why you think that, if you want to. It's okay to not know the answer. It's okay to get it wrong. In fact, it's usually a better learning experience to get it wrong. So no matter what they're typing, ignore what they're typing. Ignore what they're typing, right? Just think for yourself what you think the answer is. Just type your answer. Just whatever the first thing that comes to your mind. What's your first answer? All right, you guys are all already saying the right answer. The answer is C. That's right. Same density, and then Paramo has. Each of you are saying a piece of the answer, and then Paramo has exactly the same answer. It's the same density of fluid and the same volume. So that means the buoyant force is going to be the same, because the definition of what buoyancy is, it's just the density of the fluid, volume of the object, times gravity. So they're both in water, and they both have the same volume. Shape doesn't matter again. Same volume is all that matters. So they actually experience the same buoyant force. What's the reason why we need the cord to hold the beach ball down? They have the same buoyant force, right? So why is the bowling ball not going up? I'm sorry if these questions seem silly. I just feel like this is one of the kind of questions I have to ask to help you guys understand. Why do you need the cord to hold it in? Because it's way lighter. Exactly. It's filled with air. It weighs almost nothing. Exactly. It's way lighter. Its density is lighter. Exactly. Good job. Okay, so I got another problem I want you guys to try that's related to this. So And we'll do a little setup for this one. If I need to make this one bigger again, too, I can. Hopefully that one is big enough to where you can see it. Doesn't leave a whole lot of room to write. But, this is the problem. Okay, so I'm going to give some background to this problem. We'll read the first sentence, then we'll talk about it. So, Archimedes was a Greek mathematician and scientist. I don't know if the word scientist existed back then. Maybe it did. He was certainly a mathematician. And he was supposedly asked to determine whether a crown made for the king consisted of pure gold. Okay, so the story behind this goes something like this. Archimedes' king was given a gift from someone from a different land. And the king was suspicious that this person was kind of trying to cheat him. And his friend that had given him the gift said that it was a golden crown. But the king was suspicious. He didn't really think it was gold. And so he had Archimedes, being, you know, one of the more intelligent people in the land, think on this problem and see if he could figure out a way to determine whether this problem was gold, whether this crown was actually made of gold. And so Archimedes thought about this for a few days, and the story goes that he was sitting in his bathtub, noticing as he sat down in his bathtub the way that the water rose, but more importantly, noticing that he felt lighter when he was in the tub. And so at that moment, he supposedly figured it out. He screamed, "Eureka!" and then jumped out of the bathtub, fully naked, and just ran through the streets to the king to tell him that he'd figured it out. And what he'd figured out was that he could weigh the crown first in air, and then he could weigh it in water. And the problem here says, suppose that the scale reads 7.84 newtons in this scenario right here. And then 6.84 newtons when it's weighed in water. So the question is, what should he tell the king? Which really is it actually made of gold based on these two pieces of information right here? Now, in order to cut down on the time that it takes to solve this, I'm going to give you guys a little setup of what you need to start with here. So it's telling us the scale reads 7.84 newtons when the crown is in air, right? So that's obviously this picture right here, right? This is basically reading 7.84 newtons here, and it reads 6.84 newtons over here. So let's look at this one on the left. What would the forces acting on this crown be? Tension and gravity, that's exactly right. So tension acting upwards, and the weight of the object acting downwards like this. What about the forces acting on the crown when you put it in water, though? Obviously, there's going to be tension. Let's call this tension T1 here. So you're obviously going to have a new tension. This tension is a little bit less because of the buoyant force from the water, so we'll call that one T2. There's also weight, the same weight. While the object appears to be lighter in the water, the weight that it experiences due to gravity is technically still the same. And then one more force, right? What's the other force? And buoyant, that's right. So you're also going to have a buoyant force acting up like this. And how will they be related to each other? Well, this one, obviously, the tension and the weight are the only forces, so they have to be equal to each other, right? This one, how are the three of these going to be related to each other? It's an equilibrium, right? So we can write an equation and say something like, you know, T2 plus B should also be equal to mg. Okay, that's as much as I'm going to tell you. Your goal here is to find the density of the object. Right? And, you know, I'll give you the information you need, which is that, remember that the buoyant force is going to be equal to the density of your object, or sorry, the density of the fluid times the volume of the object times gravity when it's fully submerged, right? Okay, so given these three equations, see if you can solve for the density of the object, okay? And I guess I could throw one more equation here, which is the mass of the object is basically density of the object times volume of object. That's the other piece you need. This might take a little more time, so I might give you guys I'll give you five minutes and see if how you're doing, and if it's not enough time, I'll give you some more.
See if you can figure out what is the density of the object, and then the next step would be to figure out, is that gold?
Okay, I'm going to mute my mic, but if you do have questions, I'm watching the chat and I'll answer them. That was very fast. I'm impressed. Okay, everyone keep working. much time has that been? Has that been enough time? Anyone have an answer yet? Even if it's wrong, or give it a shot. I thought that the answer that On put in was right. I was gonna say I thought the answer was correct. I think maybe she had taken it out or taken it back just because maybe she was afraid like she'd done it too quickly. But it was the right answer. Oh, you thought it was wrong because it wasn't, so it's not, right? What's the actual density of gold? So the answer, because anyone watching on the video on YouTube wouldn't be able to see, the answer that someone put down was that the density of the object ends up being equal to about 7,840 kilograms per meter cubed. And I think that it's, yeah, so, okay, so the density of gold, so we'll just write AU here, is 19,000, so it's about half the density of gold or so. A little bit more than that. You could probably figure out what this density is, too, I think. Or if it's a mixture of densities. Something tells me it's like the density of maybe copper 10 or something like that. I don't know. Okay, so just to talk about maybe how you guys did it. I don't know how did you guys solve for the volume of the object first? That's what my students earlier had done. Is they solved for the buoyant force and then they solved for the volume of the object. Does that sound kind of like what you did? Yeah. So this equation tells us that you equate the equations, right? You say, okay, well, they're equal to mg, so T1 is equal to T2 plus B. So if you do T1 minus T2, that's equal to B. But T1 minus T2, the difference is just 1 Newton, so 1 Newton is then equal to buoyant force, but buoyant force, and I'm doing this kind of fast because I want to cover one more topic here before you finish. Kilogram per meter cubed, and then that's multiplied by VO, and then G, you guys know what G is, 9.8, right? So 1 divided by this, you end up getting the volume of the object from that, and then once you know the volume of the object, you can sub it back into this equation, or this equation if you want to, because since T1 is equal to mg, we set up here m was this, so it's also equal to rho naught v naught times g, and you can solve for rho initial, rho naught ends up being equal to T1 divided by rho naught, or sorry, divided by v naught g, and then that's where you get the answer that you guys got. Okay, so that's kind of a nice little problem. I really like that one. It's a problem we do in Physics 2A as well, at least when I teach it. Okay, does anyone have any questions? Okay. The last thing I want to mention is partial submersion. Where did our picture for that go? Ooh, there's a big gap here. This situation right here. Okay. So let's talk about an object that's partially submerged, and in particular, what we want to talk about is, we're going to get to that question in a second. We're gonna talk about the fraction of the object that's above the surface. So we go back to our standard picture that we've been talking about in this class. You've got your vessel, and now we're going to have a water level here, and then we're going to have something that's floating in the water, maybe a piece of wood or something like that. Okay. We've got an object that's floating, and the water level is right here, right? And now what happens is that only we call this partial submersion. This is what happens when things float naturally, right? You think about an ice cube sitting in water, it floats on the water, right? Icebergs float on water. Piece of wood, you put it in water, it floats, partly in and partly out of the water. Boats, right? The whole of the boat's underneath the water and the rest of the boat's on top of the water, right? You've got some amount of the object that is underneath the water here, okay? And we're going to call that volume in that region right there, up to the surface of the water. We're going to call that the volume displaced, okay? So that stands for just the volume of fluid yeah, the volume of fluid displaced. Another way to put it is it's just basically the volume of the object that's actually below the surface, right? Now again, we analyze forces. We've got our buoyant force going up like this, and in this case, we've got the weight of the object pointing down. But if it's partially submerged and there's no external forces acting on it, then that means that the buoyant force is basically just equal to the weight in this case. All right. Now you could also think that you could put an additional weight on top of this, and that would do what? If I put an additional weight on top of this object right here, what would that do to what's happening here? Would the object rise up, or would it go down? It would go down, right? Just like you step into a boat, the boat goes down. In this case, though, it's just the buoyant force is equal to the weight. You're going to have problems where, like, someone's going to step onto a barge, and the barge is going to go down. You'll have to figure out, how much is it going to go down. But you'll do the same thing with relating forces. So the buoyant force is equal to the weight, but we know that the buoyant force is related to the density of the fluid multiplied now by the volume displaced, the volume of water that's actually below the surface of the water, or the fluid, and then you have to multiply that by g. The weight of the object is density of the object times volume of object times g. So the particular ratio that we want to get is if I take the volume of the object that's displaced, and I divide by the volume of the object itself, the g's cancel. This is going to be related directly to the ratio of the density of the object to the density of the fluid. Now, if it's floating already, what do we know about this ratio on the right-hand side? Is it going to be equal to 1, greater than 1, or less than 1? If it's floating. Object density versus fluid density. Which one's bigger? This is going to be less than 1, right? So it's basically going to produce, we call it the fraction, f, of the object that's actually, above the surface, right? Now, you can look at really specific situations. In fact, let me pull this quick example. This is not a problem we're going to do. It's just more of a... I always lose my cursor when I'm doing this. Where did it go? This one? So this is just a kind of problem about icebergs. So an iceberg, you've certainly heard the expression just the tip of the iceberg. This is an iceberg right here. But this kind of rendering right here gives you an idea of just how little of the iceberg is actually above the water. And the reason for this is because, well, what's the iceberg made out of? It's made out of ice, right? And what's the water made out of? Basically the same substance, but it's seawater. And if you go look up the density of ice, and you look up the density of seawater, and you plug in the corresponding numbers here, you'll find that something like 90% of the iceberg is beneath the water, which is kind of interesting. Okay, so that's partial submersion. You're gonna see some homework problems related to this, which are gonna involve, like, someone steps on top of this. How much farther does it sink down? And it's really just about, you'll see. Okay, the last thing I want you guys to think about, and you can either answer this now or you can answer it another time, but more I want you to kind of think about it, and we'll talk about the answer next time. So, you're shipwrecked and floating in the middle of the ocean on a raft. Your cargo in the raft includes a treasure chest full of gold that you found before your ship sank, and the raft is just barely afloat. To keep you floating as high as possible in the water, should you leave the treasure chest on top of the raft, secure the treasure chest to the underside of the raft, or hang the treasure chest in the water with a rope attached to the raft? Assume that throwing the treasure chest overboard is not an option you wish to consider. So you want to save the gold, or whatever else is in the treasure chest. Do you leave it on top of the raft? Now keep in mind that the raft is just barely afloat, so that means, that if you think about it like this, you've got a situation where, draw a picture. So you've got your fluid, and then you've got your raft, but the raft is just barely skimming the surface of the fluid, and you've got this big treasure chest sitting on top of it. Right? So what do you do with this treasure chest? And then you're here too. Do you leave it on top and just hope that the water doesn't cause you to sink? A big wave comes over and gets pushed down. Do you tie it to the bottom, or do you put it on a string on the bottom? What do you guys think? I'm not going to say anything about the answer now, but maybe you guys can figure it out yourselves. I'd like to see kind of like what you guys think. Travis thinks B and C are equivalent. Some people are saying B. It is possible that more than one answer is correct. That is a possibility. Ultimately, the question about this is, suppose that you take this treasure chest, right? And you put it underneath here, right? Is it going to cause the raft to go up or down? Now, I could back it up in an even simpler way. What happens if we just throw the treasure chest overboard? Certainly, it's gonna float up higher, right? But what happens if we put it underneath so that it's in the water? Does that cause the raft to go up, or does it cause it to go down? So that's okay, Jeremy. That's a very good point. It sounds like an anchor, right? What happens? So an equivalent question to this would be, say I'm in a boat, I take an anchor and I throw it over the side of the boat, right? What happens to the water level on the boat? Does the boat float up, right? Or does it go down a little bit because the anchor's there? It's the exact same question, basically. Does that make sense? So the fact that it acts like an anchor, don't assume that means that it's gonna do what, like, an anchor tends to, like, make something stay still, right? But it does sound like an anchor, yeah. But would the anchor cause it to float up or float lower in the water? You got to think about it. It's all about buoyancy, right? It's also directly related to this problem if you think about it. The more the think, you less you know. Okay, so don't think too hard on it. We'll come back and we'll try to answer this. We'll try to answer this question next time, and hopefully when you come back, you'll have a solid, like, definitive answer in your mind as to what the answer is here. We're gonna stop the class now. I'm gonna keep talking to you guys, but I'm gonna stop the recording for now.